It's a real honor to welcome Paul Steinhardt back to Caltech. I say back because Paul was an undergraduate here several years back, and he was voted the most distinguished alumni, I think, in 2014. So you can pick up some copies of the calendar are still around, featuring Paul's likeness. No, I don't know if they have those, but they should. So Paul's, of course, as Joe mentioned, one of the founding fathers of the inflationary paradigm. But what I think makes Paul so intriguing and such a intellectual maverick is that he is sort of obsessed with this notion of how do you actually verify a prediction of a model, or how do you determine if a model is a scientific and therefore in some sense falsifiable scientific theory. And to this end, he's not only an expert on this, he not only predicted some of the first notions of the first workable model of inflation, new inflation, back in the 80s, but he also made some of the first predictions with his students, Robert Crittenden and others, of what we now call B modes. They weren't called B modes back then, but how gravitational waves would imprint a signature on the cosmic microwave background radiation. So he's, of course, well versed in that. But I think what's so special about having him here is to have this kind of alternative and perhaps pleasing model to many of us who seek to falsify models as much as we should seek to try to prove models. And I think one of the ideas that we'll hear about today from Paul and from Anna later on this evening is some complementary reasons which give motivation and rationale for those of us who build experiments to look for B modes very emphatically. So thank you, Paul.
Thanks. It's always thanks, Brian. It's always a pleasure to come back to Caltech. Yeah, so as Brian said, what I'm going to try to do today is give you some general comments about cosmological predictions. The basic theme of this talk is that although it would be very nice if our understanding of theory were as good as presented by the previous speakers, actually the situation is rather different. So when we're talking about experimentalists and observers, we can ask, what can they expect of theorists? Well, what they often get is theoretical hubris. And theoretical hubris is not necessarily a bad thing. It can be an inspiring thing if we have good control of our theoretical ideas, and we can use those ideas to explain things we already know, and then from that we derive some predictions. It's good for theorists to strongly state that you should go out and measure those things. That's inspiring. That's a nice way that experimentalists and observers can interact with theorists. But there are other times when hubris isn't called for, and I think that's the current situation in cosmology, where maybe there's more humility called for. Because the fact of the matter is, as we'll discuss, our current understanding of what our theories predict is unclear. The leading idea you've been hearing about today, the Big Bang inflationary idea, we're not even sure if it makes any predictions at all, as we'll discuss. And in terms of alternatives, although several of us, including Anna's here today, are working hard to work out what the predictions of those theories are, there are still open questions. So this is an interesting time more of humility for theorists, where I would say the experimentalists are ahead of the theorists. It's easy to tell the experimentalists what they should be doing, measuring the heck out of everything you can about the cosmos, every single one of the things you're already going after and other things that we might dream up going forward. But in terms of predictions, I think one should have some patience and wait for theories to develop more than they are now. So let me begin with inflation. So we're talking, we've heard a lot about inflationary predictions. Now, just commonsensically, what a prediction means is it's a kind of generic outcome, where generic really means generic, okay? What typically should occur for typical initial conditions, for example. But it's well known that inflation itself, in order to start, requires very special initial conditions coming out of the Big Bang. Even if I give you the basic ingredients you need to drive a period of inflation, that is to say, I give you an inflaton field, and I give you the potential of your choice, that's not nearly enough in order to get what you need. You need to have the initial conditions of that field be quite special. It has to sit in a certain space in that potential over a very large region of space, large compared to the horizon. And it needs to have a very particular velocity. Otherwise, you get a different result. So that means that most initial conditions give you something different. In fact, most initial conditions give you no inflation at all. So even though I gave you the ingredients, no inflation, given general initial conditions coming out of the Big Bang, is more likely than inflation. And then if I say, no, I'm going to throw out the ones that give me no inflation and just talk about the ones that give me inflation, well, because inflation, in order to give you a flat and smooth universe, doesn't just require a little inflation, but a lot of inflation, it requires very special initial conditions. So in fact, what I would call bad inflation, insufficient inflation, is more likely than the inflation that you were hoping for. That is which means that there's no reason to expect, even though I gave you the inflaton and the potential, to have a flat universe. Not flat is actually more likely in terms of initial conditions than likely. That's the actual prediction of inflation. Well, actually, that's not quite right, because we know something else about inflation. Once I've given you this potential in the field and all that, that's not the end of the story. There's another effect that kicks in, which is known as eternal inflation. That is to say, whether you like it or not, the same quantum effects that produce the fluctuations that you thought you wanted also produce fluctuations you don't want that keeps inflation, which produces a quantum runaway effect that keeps inflation going forever. And this quantum runaway effect leads to the effect that we call the multiverse, in which instead of inflation ending, it continues forever. It produces patches of space which span all possible cosmological properties. So in such a multiverse, if we ask the question, what is the generic outcome? The only thing I can think of that's generic that comes out of inflation is the multiverse. Anything else, any other measured quantity, whether it be curvature, the spectrum of thermal fluctuations, the smoothness, anything you would name, okay, will as often happen as not happen. And there is no measure or no way in principle of distinguishing which is more likely than the other. So no prediction in terms of the things you are measuring can be made whatsoever. So if we're thinking about testing inflationary models, and we're going to put them on plots like this, here's a plot of the tensor to scalar ratio versus the tilt, okay, we should be careful when we talk about models which produce eternal inflation in the multiverse to leave them off the plot, because they don't produce a point on that plot. They allow any possibility on that plot with equal probability. So let's take off the ones that produce a multiverse. Well, that's everything. Okay? Every model that you've heard about, virtually every model you've heard about, produces a multiverse. That's how generic the multiverse is. So these days, a lot of the focus is on potentials of this particular type, the so-called plateau potentials, because ignoring the multiverse and ignoring the initial conditions problem and just doing a little calculation, this is somehow the simplest model preferred, and that's the target that we're going after, that some people think they're going after when they're trying to measure tensor to scalar ratios of 1 part in 10,000. But this model definitely, with its long flat plateau, definitely produces the conditions for multiverse. Flatness is exactly the condition that produces multiverse conditions. Can one escape it? Well, one can in principle try to escape it, and that's what Slava Mukhanov suggested in a paper in which what I call the Great Escape, an attempt to try to escape from the multiverse, although it's not going to be generic. You have to do something rather odd to do it, and what he introduced was a wall. Okay, so there's kind of a Trumpian solution to the multiverse problem. Okay, so he introduced a wall, a place where the potential actually diverges. Because why does he do that? Because it cuts off the flat part of the potential, which is where the quantum fluctuations emerge from that eventually lead to eternal inflation and the multiverse. But you can ask the question, okay, I will no longer just consider generic inflation. I will only consider inflation with walls, okay? What does that gain me, okay, in this story of Rn versus Ns? And it turns out it actually doesn't gain you that much. So what we've done over here is we've produced again a plot of R and Ns, but this time you notice the R axis is now logarithmic, so it's covering a much larger range. And then I've shown in yellow the Planck contour, what is observationally allowed. And then we're essentially moving the wall, from place to place along the potential. We're also following a special rule, which you could argue, which is quite arguable, which is we're insisting that we release the inflaton field at the very top of the potential where it's equal to the Planck density. That was actually Mukhanov's suggested rule for solving the problem. And what you observe is that we cover a trajectory in the RNS plane depending upon where we put this wall. So in particular, if we put the wall only, so if you put the wall 29 Planck units, along this plateau, that corresponds to the top of the potential. That's pretty far back, but that's not nearly enough to take us to the yellow region. We're getting a value of R there, which is bigger than 0.5, already observationally ruled out. As we go along the contour, we're tracing a curve in the RNS plane. So notice that in this case, we're getting to a value of R, which is of order 1. Now, several people have said in the past that inflation can never give you R bigger than 0.97. Actually, Mukhanov is one of those people. But you see, this very model does that. So that rule actually doesn't apply. We're free. If we continue our way around the contour, we eventually reach a point, if we push the wall back to 500 Planck units, where we're finally entering the yellow region, but we can't go very far into it because the moment we go far into it, we've moved the wall so far back, we're back in the multiverse problem again. There's actually only a tiny region in between those two red spots over there that is both consistent with what we observe and avoids the multiverse. That's the only model I know that avoids the multiverse and actually makes some predictions, okay? Assuming that you began with the field at rest at the top of the potential. Now, if I didn't assume that, and there's no really reason to assume that, I would soon discover that actually I can open up the whole RNS plane by simply varying. Here all I'm doing is varying the kinetic energy I have to begin with at the top of the story. So, even in cases where I try to remove the multiverse, I get another kind of unpredictability which traces back to my lack of knowledge about the origin, about the Big Bang and what the conditions are coming out of the Big Bang. So what are the lessons that can be drawn from this? Well, the first is that we should be very skeptical when we say inflation predicts anything. It may be that some of us, myself included, have written papers that inflation predicts X, Y, and Z. Okay, the fact that humans wrote papers because they believe that to be so doesn't mean the theory really produces that. We've learned something about the theory in the meantime. It ain't so, okay? What I've presented to you is our best knowledge of the theory now. So it's time to move on and come up with a better idea. So what lessons can we draw from this? I would say that you want to watch out for models which, in any point along the evolution of the universe, encounter a stage where quantum fluctuations dominate over classical. Whether it be the Big Bang, which is supposed to be a quantum-dominated regime, or it be a multiverse, which is another kind of quantum-dominated regime. Because then the theory can be truly predictive. That's a guess, so that's my conjecture. Based on that conjecture, you're led to, I believe, a natural subset of possibilities, one of which is the one shown here. A universe which, first of all, avoids the Big Bang. So instead of being a cosmology with a bang, it's going to be a cosmology with a bounce. So what happened 14 billion years ago was not convergence to a singularity, but there was a bounce, which took us to an earlier period of contraction. It shouldn't just be that, but it should be non-singular. That is to say, it shouldn't be that we collapse all the way to a regime where quantum effects take over, or quantum gravity effects take over, because that will lead to some inherent unpredictability. And so that means its background evolution should be effectively classical, described by classical deterministic equations with small quantum we still need quantum fluctuations, but they would always be small corrections to what is a dominantly classical process. So in this sense, it was like what we thought inflation was in the 1980s. That was supposed to be classical with small quantum fluctuations. That's before we discovered the multiverse effect. So here we're asking, can we do something different? So one way of illustrating this story is with a kind of diagram that Anna and I have recently introduced called a wedge diagram. So the idea of the wedge diagram, it's just simply a way of plotting what's happening in your cosmology with a simple, wedge, in which we use the wedge to describe what happens to this patch of space over time in your cosmology. So this example of a wedge diagram is supposed to be describing Big Bang cosmology, the standard Big Bang cosmology, where on the right, the arc represents a patch of space, the size of a patch of space, say the size of the observable universe. when the scale factor, we'll choose the scale factor to be 1 at that point. And the wedge is telling us what happens to the patch size going back in time. It just scales, the patch size just scales with a scale factor. So at an earlier time when the scale factor was a half its size, that arc is just half its size. That's representing it would be a smaller size. At earlier times, yet smaller. At earlier times, yet smaller. Okay? So that happens, that's what's happening to a patch of space in Big Bang cosmology. But there's another important entity besides the patch size, which is, but notice that, I should say, that these arcs converge to a point. That's the Big Bang. That's the singularity. That's the singularity problem that inflation doesn't pretend to solve, but is a problem we should have in mind. It's always been there in Big Bang cosmology. A second important quantity is what we call the horizon size. Now, the patch size is telling us something about geometry, the stretching of space. The horizon size is a feature of general relativity. It's telling us the relationship between the horizon, the distance, maximum distance we can see, and the stuff that's contained within the universe. The horizon size, or the Hubble, or inverse Hubble parameter, scales like the scale factor to a certain power, epsilon. Well, that epsilon depends on the kind of energy and matter that's dominating the universe. That is to say, it depends upon the pressure and the energy density. So if you have a universe which is dominated by radiation, epsilon turns out to be equal to 2. If you have a universe which is dominated by matter, epsilon happens to be equal to 3/2. The important thing about those two numbers is that they're both bigger than 1. The fact that they're both bigger than 1 means the horizon size is growing at a power, epsilon bigger than 1, or at a rate faster than the patch size. So if I draw the horizon size on here, it's going to grow faster than the patch size going forward in time, or shrink to 0 faster than the patch size going backwards in time. So that's the horizon size in this picture. And what it illustrates is that going back in time, when we follow the patch size, both the patch size and the horizon size are going to 0, but at different rates. And the fact that the patch size goes to 0 at a slower rate means that if you look at any picture past, going backwards, it's larger than the horizon size. And that's where the mystery comes from. Why should, when we look back in time, the universe be so uniform when it's larger than the horizon size, ever more so as you go back in time? That's the source of the horizon problem. Another feature that we know is when we look back in time, we see these hot spots and cold spots, which we need to explain. The hot spots and cold spots have this peculiar, nearly scale invariant spectrum of perturbations that needs an explanation. But it's not just that it needs an explanation in terms of why is it nearly scale invariant. Among those spots, because it's scale invariant, are spots which are larger than the horizon size. So particularly important to explain is how do you end up with hot spots and cold spots which are super horizon size among that scale invariant spectrum. Then there's the cosmic curvature. So when you're looking out in space, the cosmic curvature, the degree to which the universe appears to be curved, is related to the ratio between the horizon size, how far you can see, and the radius of curvature. If the radius of curvature is huge compared to how far you can see, you can't detect the curvature. It looks like the universe is flat. Conversely, if the radius of curvature is small compared to the horizon size, it's easy to detect the curvature. So the key is this ratio, the horizon size to the curvature radius. Now the horizon size grows as a to the epsilon. The curvature radius just scales with the expansion of the universe, so it just goes like a. So in fact, the cosmic curvature, the degree of which it grows, or it's easier or harder to see the cosmic curvature, just depends upon this ratio, a to the epsilon over a. Well, if epsilon is bigger than 1 and a is growing, then this number is growing. It's been growing throughout the history of the Big Bang. So it's grown, in fact, by a huge exponential factor since the universe is at the Planck density. So it should be really clear now that the universe is curved, but it's not. We don't observe the curvature. And the only way that can be is if for some reason coming out of the Big Bang in this picture, for some magical reason, it wasn't curved in the first place. And we have no good reason why that should be so. That is in this diagrammatic picture, the flatness problem. So here I've just reviewed, using this wedge, ideas that we know of, the famous cosmological problems of the Big Bang model. Now we want to try to solve those problems. We want to try to solve them all 4 of them, including the singularity problem. So if you think about it a moment, and you weren't influenced by anything you had heard before, the first thing you might think of is this idea of a bounce. To keep the right-hand picture, this is the lambda CDM model. We don't want to get rid of that. But get rid of the front end, which is causing all the problems, the singularity, and the fact that the patch size and the horizon size are shrinking to 0. And if you have the universe bounce, well, this is what you end up with, okay? So we see in the white, we see that the patch is first going backwards in time. It's first shrinking according to the scale factor, and then it bounces and then is growing with the scale factor. So that's the patch size of the universe. It just scales like the scale factor. The horizon size scales like the scale factor to the power epsilon. So going forward in time, because the universe is shrinking, a to the epsilon is shrinking, and because if epsilon is bigger than 1, then in fact it's shrinking faster than the patch size. So we see the horizon size is enormous and shrinks faster than the patch size. And then, following the bounce, the story just continues forward. Now the horizon size grows faster than the patch size. So something interesting immediately happens, which is before, when we stop the picture over here, okay, the patch size, which is the white boundary, was always bigger than the horizon size. With a bounce, you just go back a point in time and it inverts itself automatically. There's a huge horizon compared to the patch size. It's causally connected. It's no longer a mystery now why the universe it's no longer a problem that the universe wasn't causally connected in the past. It was causally connected in the past for an arbitrarily long period of time, and that's sufficient to make it smooth. In fact, it was only a short period of time, a finite period of time, cosmologically speaking, when the patch size was bigger than the horizon size. Only this interval between here and the present. So, what about the cosmic curvature? Well, we said the issue with the cosmic curvature was this ratio, horizon size to curvature size, was growing enormously as we were in the expanding phase. But now in the contracting phase, it shrinks enormously. So a period of contraction is a super flattener in the sense that by the time you get to the bounce, the universe is super flattened before you even reach the bounce. And although it begins to deflatten after the bounce, there's been so much suppression of the curvature leading up to that point that it remains cosmologically flat to measurement, to our ability to measure it today. A sort of similar idea to the way inflation was supposed to work, but here it's contraction that's doing the job, not any inflation. Now, I've drawn the picture purposely asymmetrical because, and as to say in terms of the blue regions, because there's no reason to believe that the equation of state, epsilon, is the same after the bounce as before. In fact, if your theory includes, let's say, a scalar field in it, or scalar fields, they will tend, as the universe contracts, their kinetic energy will tend to blue shift as the universe contracts at such a rate that the kinetic energy becomes very large compared to the potential energy, and epsilon goes to 3. So in fact, the value of epsilon on this side is bigger than the typical value of epsilon on this side, which makes this a particularly super smoothing mechanism. And just to illustrate how super smoothing such a mechanism can be, let's consider a universe that began with really totally random initial conditions. So what I'm showing you here, or I'm about to show you here, is a result of a calculation using the techniques of numerical general relativity, full numerical GR, describing a universe which, well, in this case, we're only showing you one dimension of the universe. It's a one-dimensional simulation, but presumably three-dimensional simulations are going to produce the same the good reasons to believe three-dimensional simulations will produce the same thing. And so over here, we're moving along real space in this one dimension. And in these curves, I'm showing you the different forms of energy or shear or spatial curvature that comprise the initial conditions. And they're completely wild. They're just randomly chosen out of our set of experiments. In this particular example, the purple curve on top, that corresponds to the shear. That's the highest fraction of energy density highest contribution to the Hubble expansion of any. We also have spatial curvature, that's the blue. We have matter, which is our scalar field, with our value of epsilon greater than 3. And this is how the simulation starts, with a really wild initial condition. And then when you let it go, well, it very quickly breaks up into one region in which you see the yellow, or matter, is dominated. Shear and curvature are totally suppressed. And there seems to be another region in the middle where shear is 1 and matter has been suppressed. But we have to do one other thing before we come to decide what's happened here, which is we have to compute the relative volumes of these two regions. And that's determined by, well, in general relativity, in this general relativity calculation, the lapse, where purple will end up being regions of large lapse or small volume, and red will be regions of small lapse or large volume. And we begin with just some random distribution, but we let it go. Same simulation, the lapse compared to the other. And what we see is the region where matter dominates is all large volume. That means exponentially large. The region of that in which shear dominates, it's a region which is gravitationally collapsed and occupies an infinitesimal region of space. So this is a super smoothing mechanism. If I had tried those same initial conditions on inflation, it would have definitely failed. Curvature would have definitely dominated over the matter in that case. So the lesson is that slow contraction is a super smooth, that contraction can be a super smoothing, super flattening mechanism. Now, what about those superhorizon spots, superhorizon scale spots? Well, normally what we expect is we can't produce fluctuations directly on scales larger than the horizon because those regions are not causally connected. We can only produce fluctuations on scales smaller than the horizon. But look, over here, the patch of the universe is smaller than the horizon, so you will produce quantum fluctuations there. Those quantum fluctuations mean that this nice smooth picture isn't quite right. There'll be, due to quantum fluctuations, small deviations in the rate of contraction as you go across that patch. Now, as the universe contracts, the wavelength of those fluctuations is going to scale with the scale factor. So they will shrink and simply follow the patch. So I follow this picture a moment longer. Okay, they are squeezing down with the patch. Okay, but there eventually reaches a point, let's say here, where now the patch has grown bigger than the horizon size. So look, that fluctuation now scans a scale bigger than the horizon size. In fact, coming out of the bounce, there it is. Again, it's larger than the horizon size. So if you begin your quantum fluctuations over here and simply follow them forward through a bounce, they're automatically superhorizon. So logically, there's not a problem with the superhorizon, obtaining superhorizon fluctuations this way. And then it's a matter of model building, just like people have tried to do in inflation, to arrange it so that they have the right tilt and amplitude. That part is still under analysis, and that's the part that Anna's going to talk about, one of the things she's going to talk about this afternoon in this afternoon's talk. Now, of course, all this depends on the bounce itself, okay? And the whole issue of the singularity problem and being able to connect the before and after revolves around what happens at that moment of contraction. And that is where there has been quite a bit of interesting advance in the last year or so, especially due to the work of Anna, who will be talking this afternoon, in which we now have the first examples of cosmological models which allow you to have what we call a classical non-singular bounce, or at least appear to allow the possibility of a classical non-singular bounce, based, as far as we can tell, based on doing linear perturbation theory around that solution. That is to say, we can show using linear perturbation theory that we can contract, bounce, and expand without producing any kind of sicknesses, illnesses, ghosts, instabilities, etc., and smoothly transit from the left side to the right side. The chances are there are several ways of doing this besides the one that Anna has been pioneering. But the fact that we now have a first example that gets us this far, I think, is really exciting. Whether or not it really survives when we do full nonlinear general relativity, that we don't run into some sicknesses that we didn't anticipate, or some features that we didn't anticipate, is the subject of current investigation. So I would love to tell you at this moment what are the predictions of this theory, but I should be careful for the reason I outlined at the beginning, okay? Because at this point, although we've made a lot of progress in developing this theory, we think we have all the working components, now we have to actually put them all together in a tightly consistent way and show that there are no problems, and then work out make sure that the predictions are, that we're sure about the predictions. So what I can tell you, just to give you just some inkling, that some of the things that we know to be true about the smoothing phase is that during the smoothing phase itself, you don't produce any observable tensor or B modes. Because the universe is smoothing the universe by slowly contracting at fairly low energy densities, the energy densities are just way too low to produce any detectable gravitational waves or tensor modes with detectable amplitudes. Also, in the simplest models, the ones which give stable contracting solutions, turns out we also don't produce isocurvature perturbations. So detecting any kind of isocurvature perturbations, which I think is another target that people should be thinking about, that's not predicted. And also these models predict that the spectrum of fluctuations produced during the smoothing phase are Gaussian. What we're not sure about, and that's the reason for all the question marks, is that when you actually solve the equations, passing these perturbations all the way through from contraction through the bounce to expansion, we're not sure whether or not the bounce itself might not leave an interesting imprint or variation on this input. And that's a really exciting question. In fact, so the situation is, as I said, at the moment, theory is ahead of experiment is ahead of theory, but we're racing to catch up, and we're hoping to catch up in the next few years before the next major step in observations are made. So the fact that we don't know the answer yet, I think, just makes it much more exciting. That means there's a lot more at stake for both the theory and the experiment. But I think at the moment it would be wise for experimentalists and observers to sort of ignore the theorists, do your experiments, and then we'll see, objectively, and then we'll see in the end what that implies for our understanding of the origin and evolution of the universe. Thank you.